Okay folks, this is the go through for the gravitational fields questions. Question 1, so we've got the distance between the Sun and the Earth, 1.5 times 10 to the 11 metres, and we just need to work out the gravitational force exerted by the Sun on the Earth. So this is just F equals Gm over R squared, 6.67 times 10 to the minus 11 times the mass of the Earth and the mass of the Sun. These are both on the data sheet for you. But I think we're currently using 5.98 times 10 to the 24 kilograms for the mass of the Earth, 6 times 10 to the 2 times 10 to the 30 kilograms for the mass of the Sun, divided by 1.5 times 10 to the 11. Don't forget to square that. If you do that, it comes to 3.5 times 10 to the 22 newtons. So the first answer is A. Fairly straightforward question, hopefully that one. Question 2. A spacecraft of mass 1 times 10 to the 6 kilograms is in orbit around the Sun at a radius of 1.1 times 10 to the 11 meters, moves into a new orbit of radius 2.5 times 10 to the 11 meters around the Sun. What is the total change in gravitational potential energy of the spacecraft? Okay, so this question is about we probably would start from the potential Gm over R, and then we'd remember that the potential energy, the gravitational potential energy, is therefore minus Gm m over R. And the big danger here is that you do R by finding the difference between these two. You must not do that. You must work out the energy here and the energy here and then find the difference. So if you're going from R1 to R2, two different radii from the Sun, what you need to do is to do, with the difference, you do R2 minus R1. So that is minus Gm m over R2 minus Gm m over R1. If you want to make your life a little bit easier there, you can factorise that. Minus Gm m times 1 over R2 minus 1 over R1, and so if you stick that in your calculator you get minus 6.67 times 10 to the minus 11 times the mass of the Sun, still 2 times 10 to the 30, times the mass of the satellite, 1 times 10 to the 6, times the difference between 2.5 times 10 to the 11 minus 1 over 1.1 times 10 to the 11. If you stick that in your calculator, it comes to 6.79, actually I've got times 10 to the 14 joules. And this is a positive number. Now of course you might get in a mess with the signs here because it is quite tricky, but what I'd say to you is we have gone further from the Sun. It's going to take energy to move us further away from the Sun. So we've got to have a positive number. So if all else failed in the exam, I would recommend you at least to understand it's got to be one of these two answers because you're getting further from the Sun. I haven't worked it out to be honest, but I suspect this 3.38 comes from using 1.4, using the difference. But you've got to see that the difference between these 1 over r's is not the same as just putting in 1.4 times 10 to the 11. So be careful of that. Okay, question 3. So, which of the following statements about Newton's law of gravitation is correct? Newton's gravitational law explains the origin of gravitational forces. Well, Newton certainly didn't know why gravity existed, he just knew the laws about it, so not that one. Why a falling satellite burns up when it enters the Earth's atmosphere? Well, again, that's related to gravity, obviously gravity's pulling it down, but it doesn't really explain about atmospheric heating, frictional heating as things travel through the air and stuff. Why projectiles maintain a uniform horizontal speed? Well, if you ignore air resistance, that's true, but that's to do with Newton's first law, not to do with gravity. How various factors affect gravitational force between two particles, and that of course is the answer, because fundamentally it's Gmm over r squared. Here are the factors that affect the gravitational force. So D is your answer. I didn't click it to do it. Let's see for you there. Okay, question 4. So the radius of planet R of a planet is R. The gravitational potential at the surface is minus 4,000. What is the gravitational potential at 2R? So this is gravitational potential is minus gm over r. We're going to our new potential v dash, which is minus gm over 2r. So you can hopefully see there v dash is a half over the original v. You might sort of look at this and think, oh, I haven't got all the numbers I need, work out the mass of the planet or something. You can't do any of that. You've got to do it algebraically. So it's half as much. So it is 1 over 2,000. Again, surely I'm hoping that you can see that it's going to change, and when it changes it must be less because you're getting further away from the centre of the planet. So D is a really bad answer. A is the answer you get if you forget it's r and do r squared. Okay, number 5. So they love these questions and they are quite tricky. But it's sort of a fairly standard technique, and when you've seen it, hopefully you can do it and you don't get caught out by these little things like they're doing, not the ratio of the distances from the two planets, but what fraction of the total distance. It's that kind of stuff that makes it a bit tricky. So somewhere the distance y, I'm going to put it over this side so that help you to see that this distance here is going to be more than that distance, because we're looking for a place where the gravitational field strength is 0, so the attraction to this planet and the attraction to this planet are equal. Sorry, stars, not planets, but the resultant gravitational field is 0, so you must be closer to this one. So the correct mathematical way to do this is to work out the field strength in that direction due to this planet, this star, which is gm over y squared. And then if we give this a different name, let's call that x. The other one is g times 4m over x squared. Hopefully you can see the g's cancel out, the m's cancel out, and we end up with 1 over y squared is 4 over x squared, which means x squared over y squared equals 4. If you take the square root, that gives you x over y equals 2. So x is twice as big as y, if you like. X equals 2y. So this x is actually 2y. So it's split in a ratio of 1 to 2 because it's of this square factor. If you're twice as far away, if you just look at this planet for a minute, it's 4 over 2 squared. This is 1 over 1 squared. Gives you the same gravitational field. You've then got the added complication that once you've worked that out, you go back to the question, it's not this ratio, it's y over d. So it's y over this total distance, but the total distance is 3y. So it's y over 3y, which is 1 over 3. So the answer to question 5 is B. Okay, question 6. A planet has a radius half of the Earth's radius and a mass a quarter of the Earth's mass. What's the approximate gravitational field? So this is G, the gravitational field strength is gm over r squared. The mass is a quarter, so this is g times a quarter of the mass. Half the radius, so r squared over 2, so that is gm over 4 over r squared over 4. If you multiply the brackets, the 4's cancel out and you just get back to g. So it's the same as the Earth, so the answer to question 6 is C. Okay, the distance between the centres of the Earth and the Moon is 3.8 times 10 to the 8 metres. The mass of the Earth is 6 times 10 to the 24. The mass of the Moon is 7.4 times 10 to the 22. Spacecraft of mass 10 times 10 to the 3 kilograms is moving along a line joining their centres. At what distance from the centre of the Earth would the spacecraft experience no resultant force due to the Earth and the Moon? So this is the same as the earlier question, just in a slightly different way. The physics is the same. So we're looking at some distance, let's draw ourselves a little picture, Earth and the Moon. This distance here is 3.8 times 10 to the 8 meters, and we're somewhere over here, and the resultant gravitational field strength is 0, which means we get 0 resultant force. So the force towards the Earth is G times the mass of the Earth times the mass of the spacecraft over the radius from the Earth squared. Remember, this is the radius from the Earth, distance from the Earth, not the radius of the Earth. And that's going to be equal to G times the mass of the Moon times the mass of the satellite over the distance from the Moon squared. Okay, so that's the force in that direction. The first thing you'll notice is they've been a little bit naughty here. They've given you this mass which you don't need. The mass of the satellite cancels out. The G, Newton's gravitational constant, cancels out. So that gives you that the mass of the Earth over the mass of the Moon is the distance from the Earth squared over the distance from the Moon squared. So if you put the numbers in, that gives you that the mass of the Earth is 6 times 10 to the 24. So 6 times 10 to the 24 divided by the mass of the Moon, 7.4 times 10 to the 22. And that is normally stated as 81, although I think that comes to 82 point something. So if you take the square root, it's 9.1, just running out of room there, 9.1, sorry, let me go back a sec there. So the mass of the Earth over the mass of the Moon is 82, so we've got 82 is the radius from the Earth squared over the radius from the Moon squared. So if you take the square root, the distance from the Earth over the distance from the Moon comes to 9.1 over 1 if you like. That means that we're 9.1 10.1ths of the way through. Usually that work this out, so this comes to 9 over 10. So we're 9.1 over 10.1 times 3.8 times 10 to the 8, and that is 3.4 times 10 to the 8 meters. So quite a lot of work to do there to do that properly. What I would say is if you're struggling for time and you look at this question and think, oh, that's quite a lot of work to do for my 1 mark, well, where have you got to be? Look at the picture that you've drawn. If you've got this idea right, where's that? Well, 3.8 times 10 to the 8 is all the way over here, so you're not there. And 3.8 times 10 to the 7 and even 4.8 times 10 to the 7 are over here somewhere. So really this is the only sensible option they've given you. So if you were looking for a shortcut, maybe you can see that's the answer without having to do it properly. But nonetheless, obviously we should be trying to do it properly if we can. Okay, question 8. So satellites X and Y orbit the Earth at R and 4R respectively as shown. Which statement is incorrect? I put it in bold for you, but let's remind ourselves we're looking for the one that's wrong. So the speed of Y is greater than the speed of X. Well, if you think about the planets, hopefully you know that Mercury is whizzing around close to the Sun, whereas Pluto or Neptune is going around much more slowly in the distance. You can prove this is wrong if you like. The speed of Y is less than the speed of X. You would have to do that the force is gm m over r squared, and that force needs to be mv squared over r. So if you rearrange that, you get v squared is gm over r. So the bigger the r, the smaller the speed. Turns out that this one will actually be going at half the speed of that one. So A is the answer. If you want to look at the other ones, the time period of Y is greater, it's going slower and it's got further to go, so it's going to take longer to get round. The potential energy excuse me. The potential energy of Y is greater than the potential energy of X because you've gone further away, it's taken you extra energy to get up there. And the gravitational force acting on Y is less than the gravitational force on X because you're further away from the centre. So you should hopefully be able to see that these ones are all wrong. Oh, sorry, are all true, as well as knowing that that one is incorrect. Number 9. So this is a gravitational potential energy against distance graph. The graph shows that the gravitational potential varies with the distance between two planets K and L of the same radius. Okay, so obviously you look at the graph here. This is a bit, you'll see this graph like the Earth and the Moon. At the surface, this has a lower gravitational potential energy, which tells you this has got a bigger mass than this one. Okay, so the first thing you've got to notice, the mass of L, we're looking for a correct statement this time, so the mass of L is greater than the mass of K. That's wrong. That's told by the fact that there is, it takes more energy to get off the surface of this than this one. So that one is false. The gravitational field strength at the surface of L is greater than the surface of K. So this is the field strength, not the potential. So again, this goes back to the first one. If you know this one's got more mass, then the gravitational field strength at the surface will be more on this one. So that's not true. The escape velocity from planet L is greater than that from planet K. Well, if you look, the escape velocity was to do with having enough energy to get you off the surface to infinity. So it's this amount of energy that you need. So it will be easier to get off L, so smaller. More work must be done to move a mass of 1 kilogram from the surface of K to a distance point. Well, that is what this is again, so D is the correct answer. Okay, question 10. The Earth can be assumed to be a uniform sphere of radius r. What is the density of the Earth? So you've got to really look at the answers and see that they've got a little g in here. So what we're looking at is g equals g sorry, not a second m with g equals gm over r squared. But density is not there, so you also need to know the volume of the sphere is 4/3 pi r cubed, and therefore the mass of the sphere is 4/3 pi r cubed rho. So if we go back to this one, g equals g times 4/3 pi, they've used a big R, so r cubed rho over r squared. Notice the first thing you can do is cancel the r squared with two of those r's, so that gives you rho equals, take the 3 up with the g, 4g pi r, and that in a slightly different order is answer A. Okay, question 11. A satellite X of mass m is in orbit around of the radius r, but planet of mass m. What is the kinetic energy? So this is g m over r squared. That's the force is equal to the circular motion mv squared over r, and we want to use the v squared one because as soon as we saw kinetic energy, we should have thought that the kinetic energy ek is a half mv squared. So you'll notice the m's cancel out here and one of the r's cancels out, and we get that v squared is g m over r, but we want a half mv squared, so we've got a half times m times gm over r. And again, if we look over there, we've got a capital R, so the kinetic energy is ek equals, to put it in the order they've got it, gmm over 2r. So the answer is A. Okay, number 12. So the distance between the Sun and Mars varies from 2.5 times 10 to the 11 to 2.1 times 10 to the 11 to 2.5 times 10 to the 11 meters. When Mars is close to the Sun, the force of gravitational attraction between them is F. What is the force when it's furthest apart. So this is, we're looking for a ratio here where we've got the force when it's furthest apart divided by the force when it's closest, which is our F here. How big is the force? Well, the force is Gm over, Gm, so that m is the mass of the Sun times the mass of Mars, divided by the distance between them, so the furthest one, this will be squared, divided by Gmm over the radius when they're closest squared. The GMMs cancel out, but be careful with your algebra here, don't just cross out the top and the bottom. You need to sort of turn this one upside down and multiply it properly. So the ratio, the radius when they're closest squared over the radius when they're furthest away squared. So this is closest is the 2.1, so 2.1 times 10 to the 11 squared over 2.5 times 10 to the 11 squared, and that comes to 0.71. So the force is 0.71 times the original force when they were closest. So 0.71 FC if you like, but they're called FCF. Again, if you're struggling for time or if finding some of these questions quite difficult, look at the possibilities. What is the force of gravitational attraction when they're furthest apart? Well, it's got to be less than when they're closest, hasn't it? So again, if you put the answer B, at least that's a sensible possible answer. C and D are poor answers really, because you're saying that the force is bigger when they're further apart. Okay, another one of these sort of questions with two objects and looking for where the force is 0 in the middle. So again, same process. If we put where it really is, which is over here somewhere, because they've rather confused you, they've put a not to scale here, but they've put it here, it's definitely going to be over that side. This distance here to this distance here, so the distance from Pluto and the distance from Charon or Charon, depending on how you like to pronounce it, and this is 9 to 1 in terms of the ratio, so the Charon has got a mass of 1/9 of Pluto. So we can say that this force in this direction is G m over dp squared. This is G times 1/9 of the mass, so m over 9 m over dc squared. So we get, it might be easier actually, I'm going to call that 1 and we're going to call that 9m over there, so we get 9, all the rest of it cancels out, so we get dp squared over dc squared. So we take the square root, so we get 3 is dp over dc, so this is 3 to 1. Again, we've then got the problem that we're not doing this, we're doing what is the distance x from the centre of Pluto as a fraction of the total distance, so it's 3 to 1 ratio, so it's 3/4 of the way there. So the answer to question 13 is C. Okay, question 14. So the diagram shows equipotential lines. I always think that, you know, this looks like quite a confusing question, but if you just think of equipotential lines as being like contour lines on a map, there's a hill somewhere here, and these are the lines of equal height if it was the Earth's surface, which is what a contour line is. So if you put something there, and this is a contour line, it's not going to roll along the contour line in either direction, it's going to roll down the hill. Well, down the hill is perpendicular, so then all you've got to work out is which way. So that's where the numbers help you. So this is minus 1.5, this is minus 2, so this is a lower potential, so that's closer to the object, that's the downhill if you like. So it's going to roll in this direction. It's probably going to follow a path something like this, but it's got to go perpendicular to these contour lines. So C is the answer. And the last one, but by no means the easiest one. So which graph shows the relationship between the time period and the orbital radius of a planet around the Sun? So this is T and R. Let's just remind ourselves of the derivation of Kepler's law, which is very important. So we've got the force on something going round the Sun, gmm over r squared, and we've got the force required for circular motion, m omega squared r. So what we do is we cancel out the little m's, and we get gm over r cubed is omega squared. But omega is not in here, so we have to remember that omega, the angular velocity, is 2 pi over t. So gm, just move up a little bit, gm over r cubed is 2 pi over t all squared, which gives us Kepler's law. I'm going to write it up in the middle of here just so you can see it easier. T squared equals 4 pi squared gm, none of that really matters, r cubed. So Kepler's law, t squared is proportional to r cubed. So if you look at these graphs, which one of those is going to give us a straight line? So if we plot t against r to the 2 over 3, that's a sneaky trap, that is, because t is proportional to r to the 3 over 2. So if this had 3 over 2, that graph would be correct, but it doesn't. If we do log t against r, then what we're plotting is to just do the log of t against r. That's not going to give us a straight line. If we do log t against log r, then we can take this equation and we'll get that 2 log t equals 3 log r. So that will give us a graph with a gradient of 3 over 2. Again, t against log r isn't going to give us a straight line. So not that one. C is the correct answer.